All right. Welcome everyone. I hope everyone has joined. Um, I'm Dr. Roopam Dey. I am from the Department of Surgery, but I'm shared by the Department of Human Biology, and I'm a postdoctoral fellow in both the departments. And I am going to speak about statistics in general, but also important research components and how to manage them as you go through your MMed and hopefully future research projects. All right, so the basic topics that we are going to go through today will be optimal scoping of research. Research scoping is highly required, and it is recommended that you do it well so that you don't spend more time than you should on your research, because at the MMed level you have your exams that are coming up, etc. So that's why I thought it will be a good topic to speak about. Then comes the methodological approach in clinical studies. Um, since clinical studies, we deal with, in clinical studies, we deal with diseases, interventions, surgical interventions, and their outcomes. We need to be methodical in our approach so that we do not skip steps, we do not do something that is frowned upon in the surgical society. So that's why it is important that we learn a little bit about the methodological approach in clinical studies. Then we'll go into statistics, and we will see if everyone here or everyone who is doing research needs statistics. Some people might not, some people might, and to what extent does a researcher need statistics in their study. Then we will briefly touch upon scientific report writing, because that's something you need to do at the end of your MMed, where you need to write a thesis and or a paper. So we will go through the basics of scientific report writing, and we will just skim through preparing the topic of preparing manuscripts that are tailored to a certain journal. And if you have any questions during my presentation, please stop me, speak, and let me know, and I'll be happy to discuss and answer your question. And if you can hold those questions until the end of the presentation, that's also fine. Either way, I'm okay to answer your questions. All right, so going into the first topic, that is research scope. Um, research scope, it's a tug of war between work and time, because as I said, scoping a research can, overscoping a research can give you a lot of work in a very short amount of time, or underscoping a research can give you a lot of time, but then your research will not be substantial. So when you start out into your research journey, you speak to someone who will be your potential supervisor. It is very important to be quite clear with that person, that how much time you can give to a research project, and scope your research project accordingly, where you are not underplaying yourself or your availability, or you're not harming the research that you're going to partake in. So scoping a research is very important, be it the amount of subjects that you can deal with within the given time, the amount of writing you can do within the given time, the amount of literature review you can do within the given time, these all add up to the research scope. So when you are having those meetings with your potential supervisors, it is highly recommended that you keep these things in mind, because, as I said, overdoing or underdoing research can harm your research, or overcommitting or undercommitting your time to research can harm your other uh, sort of duties that you have during your MMed. Um, so basically, planning is as important as execution. So in the beginning of the research, you need to submit a document where you write down what you're going to do in the next 1 or 2 years, which is basically the time that you have to do your research. And then there's ethics document which you need to also submit. If you don't plan, or if you plan these the methodology to fit your given time, then the execution of that methodology becomes very streamlined. It becomes very easy. So a research project starts from a basic anecdotal evidence. So as surgeons go through their daily routine of performing surgeries, they observe certain things that spark that idea of research in their mind, or when they read a paper, that paper can spark an idea in their mind, which can lead to the formation of a research project. So it is again highly recommended that you take those anecdotal and literature evidences and back it up with more literature, with more evidence from the literature. So if someone tells you that, okay, reverse total shoulder arthroplasties are failing, they're not doing their job, the failure rates are high, the questions that you should be asking are, since when they have been failing, what is the timeline of failure, what kind of implant was used that these implants are failing, because in the literature doesn't have these evidences. So then once you have got all the anecdotal evidences from the surgeon, you then need to take those evidences and look for backup from the literature, and see if literature supports uh, anything regarding reverse total shoulder arthroplasties being failing in recent times. So literature survey and anecdotal evidences are required when you are forming your research scope. Then the next point that affect the research scope is availability of data and subject population. So some of you might do retrospective studies, and retrospective studies are literally based on whether the data is available in a form that you can use for your research. Sometimes the data that is available is not complete, is some parts of it are missing, or the data that is available um, is not stored in a way that you can use for your research. So before starting your research, you need to be aware of these facts. That is the data available in a form that I can use for my research? Do I have ethics to use that data? Do I have permission from university to use the data? Do I have permission from the patients to use the data? So if you don't go through these sort of rules and red tapes, by the end of your research, you might see that your work is sort of invalid because you did not um, do your due diligence in the beginning. And then comes the subject population. So this is more for people who will be doing a comparative study between two different populations, where they will be comparing, say, for example, the recovery rate, post-surgical recovery rate of any surgery between two population groups, one being young and the other one being old. In this case, you have to keep in mind that sample size can influence both the study, the validity of the study, and second, the research timeline. So more patients means you have to spend more time uh, getting the data points. You need to go out there, meet those patients, and get your data points. Also, on the other hand, more patients mean your subject population is strong, and hence the observation that you are receiving is highly valid. But then there comes a point where more patients does not mean better data. More patients just means you're putting more time. You're putting more time in with not significantly improving the quality of data. So again, that's another point you need to keep in mind while scoping your project, and that's why sample size calculations comes into play when you are planning to compare two different groups of patients or groups of population and draw an inference from that comparison. And the last point I want to make that you should keep in mind is that outsourcing research-related duties generally increase the timeline without influencing the scope. So in my experience, I have always faced this problem of whenever someone else takes over a part of my research and um, does it by themselves, it takes longer for me to get the results back than if I would have done it myself. So that's something you again need to keep in mind, that the work that needs to be done, try to be in control of the whole workflow so that there is limited delay in getting the results. Because if you're doing 5 steps, but then at one point you decided that no, out of the 5 steps, you're only going to do the first 3, and the last 2 steps will be done by someone else because you have other responsibilities. What might happen is that those last 2 steps will take longer than it took you for the first 3 steps, but the research scope or the quality of research did not improve significantly. So, and that can delay your sort of research outcome and your results of MMed, etc. So yeah, so in my experience, these are some points that you need to keep in your mind before you absolutely start with your research. And this is at the planning stage when you're planning your research with your supervisors, with your superiors in the department. Okay, so now sort of going into logical steps um, that you need to follow to think through your research. And during the scoping of the research, it is absolutely important that you formulate the objective of your research and the hypothesis only if needed, because a research project can happen without a hypothesis, but it cannot happen without aims and objectives. For example, if you're running a pilot study on comparing surgical outcomes of a very new surgical intervention, which no one has looked into before, then there is a very clear uh, aim and objective. The aim being you are comparing an old surgical procedure to a new surgical procedure, and the objective being you're you are detecting the patients, you are making your inclusion and exclusion criteria, you're measuring the surgical outcome depending on quality of life or healing of the bone, etc. So those becomes your aims and objectives, but not necessarily you have to create a, um, a hypothesis. Why I'm saying that is because there is no previous data on the new surgical procedure. So you will not be able to calculate the sample size that is required for you to measure the difference between the old surgical procedure and the new surgical procedure and find a significant difference. And for that, you might need a lot of patients prospectively. So during a pilot study, generally hypothesis-driven research is not performed, but aims and objectives are present. And the same for a, a, a big clinical trial. A big clinical trial will have aims and objectives and hypothesis. Like, yeah, it cannot happen without a hypothesis. But then sometimes pilot studies can go ahead without a hypothesis. So a hypothesis is like a if it is required, only then it should be used. But aims and objectives has to be defined at the stage of you scoping the research. Now, throughout the presentation, I'm going to use a very uh, I'm going to use a very easy example where we will be discussing about the height of two different population, and we will start by a surgeon suddenly observing and suggesting to you that according to his observation, he thinks that people with the age of 15 of different gender have height differences. So yeah, that's the anecdotal observation that your surgeon had. He comes and pulls you to the side, and he's like, "This is my observation. I think from the age of 15, there is a chance that male and female kids different have different heights." So then, you being a student, your job is to form a research question and scope the study. So we will go through this process in the following slides. So in your head, the research question that should come up is, is there quantifiable difference in height between 15-year-old boys and girls? So that's the research question. And yeah, so if from anecdotal or literature-based observation, an idea of research or a germ of research comes into place, and then you being the student, you come up with the research question. Now, we are in a clinical research setting, so before going forward, you need to determine which route you're going to take. And the next slide sort of gives you an overview of the different clinical research that, or the different paths that a clinical research project can take. So clinical research can be broadly divided into observational or experimental. So observational is, you measure certain clinical parameters, you compare them at one time point, you compare them at a longitudinal time point, that's like after a year, after 2 years, after 3 years. And you can also compare those things um, as a case control study or a cohort study, where you you compare two groups going forward in time where there is an intervention. You compare, in case control study, you compare two groups, one from one perspective and one being retrospective. Then in experimental study, it is mostly the studies that goes under experimental or therapeutic, interventional, or prophylactic, and these are to evaluate the effectiveness of different treatments, different sort of drugs, different health services, etc. So in our case, which is measuring the height differences between boys and girls, we are looking into observational study, because we are observing what is the height of these two groups of humans. Um, if you have a group of boys, if you have a group of girls, we are observing what is their height, and we are sort of calculating what are the differences. And then we are literally going into defining a population and figuring out rates of difference, like how many times uh, a girl was taller than the boy, how many times the boy was taller than the girl, etc. Then we are again like, okay, this is not a disease, but then if you sort of think about it, it's how likely is it for a girl to be shorter than a guy, or how likely is it for a guy to be shorter than a girl? So we are measuring that prevalence of, or the incidence of those phenomena at the moment with the study. And then the final route that we can take is cross-sectional or longitudinal. In this case, the surgeon told you that according to his recent observations, he wants to look into kids with the age of 15. So then that means that he wants to look into people from a single time point, that is the age of 15. That therefore it becomes a cross-sectional study. So yeah, so you are literally taking kids that are 15-year-old and measuring their heights and observing if there are any differences or not. So that's the clinical route or clinical research route you're going to take in if you're doing a study similar to measuring the height, the example that we are going through right now. So then again, you have done this job at night, and then next day you meet the surgeon at the cafe, and then he says, you know what, uh, let's see if these observations influence the measurements further in the years. I know at the moment you might be thinking that this cannot happen, and um, when someone comes to me with the research question will be absolutely defined the first day when the research topic is given to me. But trust me, research topics change, research ideas changes, research questions changes, and you have to be a little flexible when it comes to um, doing clinical research. So at the cafe, the surgeon tells you that, okay, let's see if these observations influence the measurement further in the years. So then you go back after you have done your work, you go back to your home, and then you formulate the second iteration of the research question. So with the first iteration of your research question, that was, is there quantifiable differences in height between 15-year-old boys and girls? With that, you add another research question depending on what the surgeon told you in the cafe, and then you come up with the second research question saying that, does this trend continuously progress as the individuals grow older? So now you're taking the same cohort of boys and girls and measuring them year after year. So from 15, you are starting. You're including them in your study at the age of 15, and then say you're measuring them until the age of 17. So you're measuring them at the age of 15, all of their heights, and then at 16, you're measuring again their heights, and then at the age of 17, you're finally measuring their heights again. Why I'm stopping at 17? Because beyond that, you won't be a MMed student anymore. So yeah. So then this research study becomes a longitudinal study. So say, for example, you performed a surgery on 10 individuals, and then you are measuring their X-ray, of you implanted a plate into someone's radius, and you want to see the healing of that patient. And if you only observe their healing after 3 months, then that becomes a cross-sectional observation. Whereas if you observe their healing after 3 months, after 6 months, after 9 months, after 1 year, and then say after 15 months and 18 months. So that becomes a longitudinal observation because the observation was performed over time, over a period of time. So similar to that, in our example, we are measuring the height of the individuals, the boys and girls, over a period of time, and hence now this study becomes longitudinal instead of being cross-sectional, which was the first brief that was given to you. Cool. So now moving to the next slide. So whenever you're measuring something, when you're physically measuring, say, um, the neck shaft angle of the femur before you implant a, a hip implant into someone, if you're measuring a neck shaft angle of a femur, it is okay to do it by yourself. Um, it's okay to do it by yourself when you are going into a surgery. But then um, when you are measuring something for research, there are different rules that you need to be aware of, which we will go into in a bit. So, important points that you need to remember when you're measuring anything uh, for clinical research is that first, your consistent measuring approach in terms of apparatus and posture is required. So, for example, if I carry on with measuring these boys and girls, you need to make sure that everyone stands in their anatomic position. Everyone is measured with the same tool, be it digital or be it analog or just um, a like a thread or a measuring tape. It has to be consistent. It cannot differ. You cannot measure one person in your whole population with a thread and the other person with a digital height measurer, if there is one. One of your subject cannot be crouching down and the other one cannot be sort of standing with their on their toes. That's again inconsistent ways of measuring. And then in actual clinical research, if you're measuring an X-ray, if you're measuring 15 X-rays of 15 different patients, you have to make sure that the X-rays are in the same plane. The X-rays were taken, um, they have the same view, their anatomical positions are consistent. I think it's a little easier when you are dealing with X-rays, but then if you are dealing with CT scans, then you have to make sure that all the CT scans that you're measuring have the same view, um, from the same angle, from the same. If you're choosing a lateral view, then all the views should be lateral. You need to also make sure that you're choosing the same slice of CT that you're measuring for all the patients. So when it comes to measuring anything in your clinical study, you need to make sure that the approach and in terms of apparatus and posture and anything else is consistent. Um, the second one being matching of age. So in this case, where we are measuring heights, we want people to be healthy. We do not want kids who have deformation to be included in the trial or in the study unless and until there is a need uh, to include people with deformation in the study and it has been defined at the scoping stage. But since we did not define, we need to go ahead with healthy subjects with matched age. Well, in this case, we have already defined that our uh, our study only includes people from 15 to 17, so they are already age matched. But say, for example, you are measuring again healing of radial plates after a surgery. So if you take patients with different age profile, if you compare a 16-year-old man with a 62-year-old man, it will never be it will never be consistent, because the healing the healing properties of the bone are different as you grow older. So those are something you need to keep in mind, that if you're comparing people from two different age groups, if you're comparing patients from with different types of fractures, say for example, uh, again taking the example of the radial or a radius plate that you have implanted, but then one patient had a hairline fracture while the other patient had a highly comminuted fracture, then their healing pattern again will differ. So those things have to be taken into account, and that's when you set your boundaries. And your boundaries in clinical research comes as inclusion and exclusion criteria. This is something you need to define with your supervisor, and um, sort of make sure that you follow them as you go through your research when you're measuring, if you're measuring something in your research. And then it is highly advisable that you have equal number of subjects in both groups. So if you're measuring two different uh, populations who have undergone two different ways uh, of surgery, two different types of surgery, then it is highly recommended to have equal number of subjects in both the groups who are age matched and preferably had similar fractures or similar injuries or similar diseases, so that you're comparing apples to apples and not apples to oranges. Um, yeah, so these are some important points to keep in mind. Um, and then as you are going through these points, you meet your surgeon again, um, and then he comes with a third idea that he does not trust computerized measurements, and he wants the height measurement to happen with measuring tape. So as we discussed before, it's not a train smash. You can um, measure using either computerized measurement or any form of crude measurement devices, given that you measure all the subjects using that same measurement system, um, so that you don't change it. There is a consistent measuring approach. As long as a consistent measuring approach is sort of utilized, it does not matter how you measure it. So, but then this changes certain points that you need to keep in mind regarding the measurement again. So when there are when certain measurements are performed physically, say for example, I spoke about measuring the neck shaft angle or the diameter uh, of the femoral head, or the length of someone's radius or ulna. So um, when you're doing these measurements for research, it is always important to have multiple observers. So say for example, for your research you need to measure the femoral neck shaft angle, and for 20 subjects, then and you choose um, a method of measuring which is manual, using certain tools that are present in a computerized environment. So to reduce bias, to eliminate bias, where you have your way of measuring but someone else in the world might not have your way of measuring. So your method of measuring can introduce bias in the measurement. Or even if you are left-handed and someone else is right-handed, and you use your left hand to measure using your mouse and keyboard, just mouse, then it can also um, introduce bias into the measurement. So it is highly recommended that when you're measuring anything for your research using manual methods, then it is important to include multiple observers. And uh, it doesn't have to be someone who like someone's special in a way to be your second observer. You can ask your colleague, or you can ask your supervisor to be the second observer, and two observers are good enough. If you include third observer, then again you're going into the region of increasing number of data points without um, really influencing the outcome of the study. So two observers are enough, uh, and multiple observers, they reduce um, inconsistencies in measurements. So yeah, so when you're measuring something physically, then make sure that you use multiple observers to reduce the bias that can happen. Um, and then once you have done all this, then um, it can also happen that um, your surgeon can come to you and um, tell you that tell you to measure um, another physical dimension, which is um, which is like if he comes to you and asks you to measure the height, and then he asks and come to you and asks you to measure the tip to tip length of the arms, where you have to measure the full um, range of the arms from one side to the other, then at some point um, you need to make a decision of if you want to include that measurement in your study, or you don't want to include that measurement in your study, because now is when you have to make a decision if you have time for it or if you don't have time for it. But my general rule of thumb is, if you have not collected the data yet and you have time for including the secondary measurement that is being asked of you, then it is a safe bet to um, include those measurements before you have collected the data. Um, that is, yeah, that's more like figuring out all the variables that you want to measure for your study and building a final research question, which now from one we have gone to three. The first one being, is there a difference in height? Is there a trend as the kids grow older? And is there is there same effect observed in the arm span of these kids? So as long as you have made your final um, research question and you have figured out all the variables that you need to measure it before you go into the actual physical measurement part and the statistics, it's fine. Um, you can include extra questions or extra observations given you have time. Um, yeah, so now we go into how you can apply statistics to your um, your research that you will be doing. So this is my very personal sort of idea of how different people see statistics. Yeah. Um, few important questions to ask before you dive into the world of statistics and sort of get lost is that, does the study really require conventional statistics? Because some studies do not require conventional statistics. Some studies, especially where the ones where you are asking patients how how are they feeling after a certain surgery, or um, if you are measuring a single group's recovery rate, and you only want to report on their recovery characteristics and quality of life characteristics, then you can literally do uh, mean and standard deviation and report on those parameters. You don't need conventional statistical comparisons to report on the observations. Or if you're doing a Delphi study, you don't need statistics. Um, and then if you think that you will need some form of statistics, then you need to then figure out, is descriptive statistics sufficient, or is inferential statistics required? So descriptive statistics are like mean, standard deviation, median, range, interquartile range, and anything that define the data. It's also otherwise called as central tendencies. So any parameter that defines your data is called as descriptive statistics, or describes your data is called as descriptive statistics. Inferential statistics is something that allows you to infer the characteristics of the populations that you're studying. Um, Say, for example, we are taking an example of measuring height of two different population group. So we might need inferential statistics to figure out if the two groups are significantly, if the height of the two groups are significantly different or not. We need to do a t-test. We might have to do a non-parametric t-test to figure that out. So for our example, we will need a inferential statistics. But then if we had only taken one group, say, for example, if we had only taken um, 15 to 17-year-old girls, and we wanted to measure their height and any not do any comparison, then descriptive statistics would have been sufficient. We could have described the mean and the standard deviation of the height for each time point, and we would have been fine with it. So then when you're doing your research, you need to be a little aware of what your aims and objectives are, and that should determine what kind of statistics you're going to need, whether you're going to need descriptive statistics or inferential statistics. Now, if you are doing inferential statistics, then the type of test is going to depend on the distribution of your data. Now, data is either normally distributed or not normally distributed, depending on its frequency of distribution. So normal distribution looks more like a bell curve, which I'll show you in the next slide, and not normal distribution uh, looks like a skewed bell curve. So depending on how your data is distributed, you either use a parametric um, testing, a parametric test, statistical test, or a non-parametric statistical test, which you don't have to literally like think about right now, because or try to remember them if I show you the slide, but just know that depending on the distribution of your data, the statistical test is chosen. So the second step towards performing inferential statistics, where the first step is to find out first if you need an inferential statistical test or not, and the second step is to find out whether the data is normally distributed or not normally distributed, and then you can select the test. And the final point you need to keep in mind is where multiple observers involved, because when measurement is performed by multiple observers, then you need to do a intra-class correlation coefficient, and it's an extra statistical test that you need to do. So it is to find out if the observers were more likely to be in the same page or not, or if they did the measurements similar to each other or not. Yeah, so that's an extra step that you need to do if there were multiple observers involved, but there is no running away from it if you are measuring something physically. So if you're measuring something physically, it's better to call your colleague and ask him to measure it as well, not with you, but like absolutely separate from you. You both of you can't sit there and talk to each other and measure the same thing. That's absolutely, then there is no point of doing that. So it should be independent measurement, and once you're done with the measurement, the statistical test that you perform to see if the measurements were similar or not is called intra-class correlation coefficient, and that's another step you need to include if there were multiple observers involved. So the next slide shows a perfectly normal distribution of data. So you have got the central line where it's is the point where there is mean, and then on the right you have 1 standard deviation, 2 standard deviation, and 3 standard deviation, and then on the left you have negative 1, 2, 3, 4 standard deviation. Now in statistics you might have heard the term p is less than 0.05, which is the clinical statistical cutoff that we use for our studies. It basically means that the data that we are comparing this this population group with, there is no chance of finding any of the other population group within the 95% um, of this population group. So they lie on the other side of um, these black dotted lines. So that's the meaning of statistical difference. And to show you what, let me just try and draw it to show you what a um, not normally distributed curve looks like. It looks something like this. A not normally distributed curve looks something like this. And for a not normally distributed curve, we are going to be using non-parametric comparative tests. And for normally distributed curve or data, we are going to use parametric um, statistical tests. Now, there is no when it comes to statistics, um, the same data can be inferred. I need to remove this. Sorry about that. Okay. So when it comes to statistics, data um, can be cut into different slices. Its data is like a cake, and you can cut it into different slices to perform your statistics. And use of statistical tests does not depend on the whole data, but the slice of the data you want to look into. So you can cut the slice of the cake in a triangular shape, in a square shape, or as half. It does not matter. Statistics does not depend on how you cut the data or how you portray the data, but then it depends on what inference you're trying to draw from comparing those two parts of the data or multiple parts of the data. So that's the beauty of statistics, that you can collect as much data as you can. Statistics will help you in inferring different questions that you want to answer with the same data. So yeah, this is basically how statistics work. Now going into hypothesis-driven clinical research. When it comes to hypothesis-driven clinical research, it's very important to set these parameters at the beginning of the study. So if you are deciding to go the hypothesis-driven clinical research way, then you need to define your null hypothesis and you need to define your alternative hypothesis. So say, for example, we can use um, our example of um, measuring height for um, of the kids. So our null hypothesis will be that there is no significant difference between gender groups from 15 to 17 years of age. And our alternative hypothesis will be that there is significant differences in height of gender groups, between gender groups, between in of the age of 15 to 17. So we need to define these two hypotheses before we start our hypothesis-driven research. So how this works is that by accepting the fact that we have a null hypothesis, our statistical tests should be designed to reject or accept the null hypothesis. So the whole point of doing statistics in a hypothesis-driven um, clinical research is to either accept where, and we accept the null hypothesis when the p is greater than 0.05, when there is no significant differences between the two groups, and we reject null hypothesis when p-value is less than 0.05, where the where the um, statistical difference is significant between the two population group. So one of the main tasks for hypothesis-driven um, clinical research is that you have to measure the sample size before you start um, with your research, because there is no point of doing a hypothesis-driven clinical research without finding out if the amount of people you have included in your study will have the effect size or will provide your study with sufficient power for um, for rejecting or accepting the null hypothesis. And for that, you need to calculate your sample size. For calculating your sample size, you need to have some way of measuring uh, the mean and standard deviation of the two groups that you are working with, and that will give you effect size. So it is highly recommended, if you are going for a hypothesis-driven research, then spend 2 to 3 months to survey the literature and find if there are similar studies that have been done before before you, and if you can find um, average and standard deviation of the parameters that you're measuring. And if you don't find any, then spend more time to perform a pilot study and find average and standard deviation of the groups that you're trying to measure. And the thumbs up rule to perform a pilot study is to have 15 individuals in the two groups that you are trying to measure. With 15, you can be confident enough to get a good sample data of the population that you're trying to include in your in your study. Because hypothesis-driven research is quite important in the clinical research world, and if you're not doing it in a way that it is done, then it is sort of frowned upon. So don't take hypothesis-driven research lightly. And one of the ways you can sort of not do justice to hypothesis-driven research is to not calculate the sample size um, to find out whether it is good enough to influence your acceptance or rejection of the null hypothesis. So yeah, that's something that you need to keep in mind. So like I said, going back to our example that we are using in this lecture, that is measuring height of a group of girls and a group of boys for a certain age. Our null hypothesis is that note there is no difference in height, and the alternative hypothesis is that there is difference in height. Now, here I'm showing you two perfectly um, normally distributed data. So the blue, we can say that the blue line belongs to the boys and the red line belongs to the girls. And what we are seeing from these two graphs is that um, the mean of the red graph lies it lies outside the p is less than 0.05 a line or the area of the blue graph. So what we can say from this graph is that we can reject the null hypothesis and accept the alternative hypothesis that there is significant difference between the two groups. There are more sort of rules to it, but then this is basically how or what p less than 0.05 or greater than 0.05 sort of mean is that it tells you how possible it is or how probable it is to find um, to find subjects from the red graph in the blue graph or from the blue graph in the red graph. So the p less than 0.05 means that there is less than 5% chance to find an individual who belongs to another group in the group that you are looking into. So for example, if you're looking into the red group and with the statistical test, you found that p is less than 0.05, then you can with high confidence say that you will not find any person from the blue group in the red group, or there is less than 5% chance of finding an individual from the blue group in the red group. So yeah, that's basically what inferential statistics tells you. But then there are other rules to this to this sort of inference. Say for example, the first image on the top, it's even though the p-value, you can imagine that the p-value is less than 0.05, there is high beta error probability. Now beta error is otherwise known as power. So the power of your inference in this case is very low. So you might find that there are people from the red group who are more likely to be present in the blue group, but which is not highlighted the uh, by the fact of your p-value was less than 0.05, because there was small effect size and very low power between of that observation. And this happens when you do not perform a priori statistical or power calculation or sample size calculation. This is a very common observation when the sample size is not calculated before performing a study. The second graph, you can see that the blue graph has moved a little towards the outskirts of the red graph. And this is a medium size effect size, where effect size is the difference between the heads of the red and the blue graphs. And here there is medium beta error probability, and it is not low powered, but then it has got less than adequate power. Now, when it comes to clinical statistics, the lowest power that you can go for is 0.8. It's and that's also in cases of very rare diseases, um, for very rare surgeries. Otherwise, studies must have power of, especially the hypothesis-driven studies must have power of 0.9 or above. So less than adequate power here means the power was less than 0.8, because 0.8 is the minimum power that you require in a study that you're trying to draw inference from. So even though in this graph there is statistical significance between the two populations, there is a high beta error probability, and which is otherwise known as type 2 error in statistical term, and it has got less than adequate power. This is more or less, the third graph is more or less the best possible outcome of a hypothesis driven statistical the effect size is large. That means that the two populations are quite far from each other. There is very less type 1 error. Type 1 error is the one that is determined by the p-value, and then there's very low type 2 error, which is determined by the beta value, and there is very high power. And here by high power, I can assume that the power was greater than 0.9, because they are so far apart. So this graph suggests that there is very low chance of finding any one from this blue graph in the red graph or under the red graph, and vice versa. That is, finding anyone is very low probability of finding anyone under the red graph in the blue graph region, in the region of the blue graph. So yeah, this is comparing two groups and drawing inference from them using parametric statistical tests. Why I said parametric? Because all these graphs, they look normally distributed. They do not look not normally distributed. So hence, if there were two groups that were being compared, the comparison would have happened using student t-test or just normal t-test. Yeah, so this is how statistics sort of compares two different groups. And now we go back to the theory of work versus time, because if we take our example of comparing two groups where we were finding their heights and trying to compare them, if we find out that no one has ever done the height comparison before, or there exists no evidence of height of a child who is 15-year-old, then we need to perform a pilot study, as I was saying before. So from the pilot study, we can use 10 to 15 participants for each group, and we can perform a priori sample size calculation. All you need is for sample size calculation is the p-value, the power value, and effect size. You can either calculate using the mean and standard deviation of the two groups, or you can use a effect size that is greater than equal to 0.5. So as long as you follow these rules, your sample size calculation should give you a number for, or number of samples in each group, that will help you reject or accept the null hypothesis confidently. Now, once you have done that, you need to just keep in mind what are the different tests that you can perform to calculate the p-value. So I've been talking about parametric and non-parametric tests. So parametric tests are performed on only normally distributed data. You cannot perform parametric test if you don't know the distribution of the data. That's why it is distribution dependent. Whereas non-parametric test can be performed on not normally distributed data, that is the data which does not follow a symmetric bell-shaped curve, or it can also be applied to normally distributed data. So this one can be applied to both, but then parametric tests cannot be applied to not normally distributed data. So generally, when I do statistics, I find the distribution of the data. If it is normally distributed, then I use t-test or ANOVA, or in terms of correlation, I use Pearson's correlation. Whereas if I find that the data is not normally distributed, then I use Mann-Whitney, Wilcoxon, Kruskal-Wallis, or Spearman's correlation to find association. Yeah, so as long as you are remembering these few tests, I'm sure you will be able to perform your statistics and find, or perform your inferential statistics and find the p-value. So there is something we spoke about where we looked into inter-observer and intra-observer variability. Now these things come into play where there are more than one observer performing a measurement task or measurement related task. Then we need to figure out how similar or how different their method of measurement or their observations were. And for that, we calculate interclass correlation coefficient, which is basically plotting their values next to each other. And the highest interclass correlation coefficient you can get is 1, but any value greater than 0.8 is considered to be is considered to be good, and you can infer from that the fact that the two observers were very similar in their method of measurement and in their values that they measured. So for inter-observer variability and intra-observer variability, you can use the same test, which is ICC, or intra-class correlation coefficient measurement. You can, in terms of performing the statistical tests, there are various softwares that are out there. There is R, there is Python, but I use IBM SPSS and G star power. So G star power I used to use for measuring or calculating the sample size, the a priori sample size, or the um, post study sample size. But now with the latest version of IBM SPSS, which is version 27, they have included power calculation protocols as well. And it is very easy to use IBM SPSS, and it's not the greatest tool to plot your data, but then it is a easy software to perform your statistical tests, and it is freely available on UCT website. And G star power is an open source power calculation tool, which is validated by in literature. So you can use it for research purposes if you cite the papers that validates it. All right, so now that we have gone through stats, you have measured everything, and now you have done your sample size calculation, you have done a pilot study, and you are almost halfway through measuring your population. And then if your surgeon meets you and tells you that he or she wants to measure another parameter, then you won't be wrong to ask them or to tell them that it's too late, because you have already measured half the subject population that you had recruited for your study, and there is no way you can measure another parameter in all of them, and there is no way you can include that into your study. So that's why it's very important that you have an agreement with the people that you are doing research with, that all the variables and all the measurements are discussed before you actually measure the parameters or you do your statistics. The moment you start measuring the parameters, you should not be changing anything on the protocol. You should not be introducing something. You should not be excluding something. Then then the integrity of research is lost, and that's not a good thing to do. Yeah, so now once you're done with your research, you have measured, you have performed your statistics, you have inferred what your results sort of showed you, and now you have to either write a thesis or you have to write a journal paper to finish your MMed. So generally, how we read a research paper is that we start with the introduction, we go into literature review, we go into methods and results, and finally we go into discussion and conclusion. When there is an abstract involved, then we read it, like we read the abstract first, and then we go to introduction, we go into literature review, methods and results, and then we go into discussion and conclusion. Well, this is not the only way to read a paper. You can also do selective reading, where if you are only interested in knowing how someone performed a study, then you can only um, read their methods and results. If you want to, if you're looking for new articles, and you're only interested in finding out new articles in the literature, then you can only read the introduction and literature review. And if you want to find out the meaning of only want to find out the meaning of someone's observation, then you can only read the discussion. So you can also do that. But this is more or less how generally in an average we read a scientific report. And the whole of abstract is sort of the whole paper is sort of summarized in an abstract. And yeah, that's basically how it is. But the writing does not happen in this manner. We do not write the introduction first, the literature review next, the methods next, and the discussion at the end. Or I must say that this is not how I write it, because it does not make that much sense in my head. So what I do is I start with methods and results, because once you methods are action items. You are performing it, so you remember it um, better while you're performing it. So it is advisable to write down the methods as you are doing them, so that it's fresh, and you write as much as possible. Because remember, one of the reasons you are writing this paper, or you're writing this report, is because if anyone wants to mimic your study, if anyone wants to perform your study on a different population group, then they should be able to perform it without any hurdles. So your methods needs to be written in such a way that anyone else can just read it and perform your experiment or your study. So it is advisable that you write it in the beginning while you are performing the steps that you're writing in methods. Um, it it also sets the correct tone for the document, because sometimes if you start with introduction and literature review, you can get lost a bit, because there is so much literature there. It can happen that there is so much literature out there on the topic that you're researching on, that you get sucked into a rabbit hole and you start writing about something that is not even related to what you're going to do in your methods. So that will be a waste of time and resources, because at the end of the day, the one of the other senior authors or one of the reviewers might come back to you and say that, okay, take all these 3 pages out, because it has nothing to do with what you're trying to say in your research. The methods do not match your lit review. So that's why it is easier to write the methods first, and then structure your literature review and introduction according to what you have done, rather than what's out there. Um, then I use a lot of images to map a story, um, and drive the previous chapters according to the results. So um, it always helps to provide a sort of schematic of in the methods, where you show that step 1 was this, step 2 was this, step 3, step 4, and step 5, where you take the reader through those steps in a schematic, and um, you can drive the previous chapters, which are your literature review and introduction, according to the results which you're observing. Um, and the final step is, do not write results again in the discussion. It is not advisable to write the results in the discussion. All your observations and all your measurements, everything should just be listed in the results. And in your discussion, you are only supposed to compare your results with literature, and you need to write the meaning of your results in clinical terms. That's the basic rule of writing results, that it should not be rewritten back into the discussion, apart from some part of the statistics where you can, if you observe that, okay, boys were taller than girls for every age. Now you need to write why they are taller, or what does it mean for them to be taller. That's what discussion is for. It's not to write again the results and fill the space. That's why it's very important to write the methods and results, so that one, you don't get lost in the literature review space, in the introduction space, and second is, you have an idea of what to write in discussion. You have an idea of which topics you want to discuss in the discussion. So that's why I always start with methods and results when it comes to scientific report writing. And then you can go to literature review. And one thing you need to remember is, literature review is uh, is not copying and pasting from previous work, because the whole point of literature review is to read, say, 5 papers and write in your own words what you have learned by reading those 5 papers. And that's what the review of literature means. In the past, I have come across papers written that were flagged by Turnitin. Turnitin is one of the softwares that UCT provides to um, measure the plagiarism percentage in a document, where you can upload the document and see if your plagiarism is high or low. So for a paper, anything above 5 to 7% is quite high. And once I came across a paper which was almost 60%, because this person had copied uh, from previous papers, even though he gave proper references, but then it was literally a copy and paste from literature, which you're not supposed to do. You're supposed to write in your own words what it is, the idea you're trying to present in the literature review, and you're trying to draw the attention of the reader and sort of lead him into the methods and results. Yeah, as I said, it should be written in your own words, and preferably when you're citing authors, um, or information that comes from multiple sources, find the initial source of information, or the the first paper which spoke about that idea, and then cite them rather than citing someone who took that idea and rewrote it in their own words. uh, yeah, because you need to credit the people who are due the credit or deserve the credit, or else cite everyone who has spoken about that idea. um, yeah, so these are some important points you need to think about while writing literature review. And generally, methods, after writing the methods and results, you should focus on literature review, um, and then go into introduction, where you define the purpose of the work, what is the need of the work, why you're doing this work, why you're spending time in from your busy schedule, uh, and sort of giving time to this work, what it is going to change if the clinical community actually need this work. So all those ideas and definitions you're going to put in the introduction. Um, so in certain papers, there is no space for literature review. It's only introduction. So introduction, in that case, then you need to combine both the ideas, that is all the previous work that was done and the need for you to spend time on this work. All all those ideas need to be written in introduction. And the point of writing introduction after methods and results is that it has got a direct connection with um, discussion, because in introduction you are writing about the previous work that was done, and in discussion you are comparing your results with the previous work. So it becomes very easy for you to find out which studies you're going to compare your work with, uh, why, and then to go into the process of finding out why your results are similar or different from previous work. And again, in discussion, you need to mention why your study was important, plus what are the shortfalls of your study, because no one's research is 100% accurate and done perfectly. We are trying to do it as perfect as possible, but then at the end, there will be limitations, especially because we are doing the research in a resource limited setting in a developing country. We always face limitations. So discussion is another is the place where you mention those things, like why your study was important, what were the limitations, and what should future studies um, look into to overcome those limitations. So there's a large crosstalk between introduction and discussion, and that's why you should write introduction and discussion almost at the same time, um, to facilitate crosstalk. Yeah, so that's the pattern of writing a scientific journal or manuscript or report, is that you start with your methods and results, you go into lit review, then you go into introduction. Sometimes you have to combine introduction and literature review together, and then finally, after you have written the introduction, you go into discussion, because there's a high crosstalk between those two sections of the document. And then once you've written everything and you're happy with it, and all your um, co-authors are happy with it, then you write the abstract. An abstract is basically taking the important points from each section of your document and then um, combining them into the abstract, which is presented at the beginning of the scientific document. Um, so so this idea you can apply to um, any form of scientific writing, but the next thing that we are going into is manuscript preparation. So in manuscript preparation, most of the ideas that we discussed now of how to write a scientific document still holds true. Um, yeah, from experience, I can say that. But then in 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 manuscript preparation, it is the one thing that you have to keep in mind is that the journal that you're writing to, they cater for different uh, different readers. So say, for example, Journal of Biomechanics will cater for researchers who are doing biomechanical study. So if your study was on the bare measurement of height of two groups, and you're writing it to Journal of Biomechanics, then you have to write it in such a way that you give the study a biomechanical spin and then write it and then send it to Journal of Biomechanics. Otherwise, the readers will not be interested in reading your manuscript, and there are high chances that Journal of Biomechanics will reject your uh, your paper. Rather than that, if you send your paper where you're measuring height of children between 15 to 17 and comparing the differences in height in genders, and you send it to um, Journal of Adolescent Health, then um, then there is higher chance um, of that manuscript being accepted, because the readers will be interested in reading what you have written. Um, so yeah, so there are different journals where you can send the same study uh, by tweaking it um, according to their writing structure that they have given, the setup, the flow. Each journal has their own referencing style. Each journal has their own formatting style, and all these are available um, in a section on the page um, the journal, which is called the guide to the author. And if you read that page properly, then you will be able to tweak your manuscript to that journal's specification, and this will not take a lot of time. Yeah. um, and finally, you need to make sure that the readers or the audience that the journal caters to, you are writing something that is worthwhile for them to read. Otherwise, like I said before, your paper will not be entertained in there by the reviewers, and they might reject it. So the ways to find out which journal you should send your paper to find the best journal for your paper. You need to um, select the journal according to your keywords. say for example, you are measuring or you're doing a study on ankle, then find a journal um, which publishes a lot of ankle research. If you're doing your research on knees, find a journal that is specific, very specific to knee. If you're doing research on shoulder orthopedics, then go for Journal of Shoulder and Elbow Surgery. And if you're doing research on um, biomechanics of a of a of a joint, then go for Journal of Biomechanics instead of going joint specific. So your keywords and the topic of your research will help you to select a journal. To make sure that your manuscript is in line uh, with the journal, try to read a few recent publications. Try to read their introduction. Try to see what kind of papers they are referring to. Uh, Try to refer those papers if they are in line with your study, because nothing gives more pleasure to a reviewer and the editor of a journal if they see papers from uh, their publication being referred to. Yeah, in experience, I can tell you that. Then in discussion, refer to important studies that their uh, publication house has published, and compare them to your study, compare them to your findings. And these tricks can actually help you get into the journal that you are trying to publish your paper in. Apart from writing a very decent manuscript with very limited grammatical errors, a paper with um, good methodology, where ethics was followed, um, where the methods were described in such a way that anyone can follow it and mimic your study. So once you have got the basics right, these are the major tricks um, to get into a journal that will publish your paper. Yeah, that's it. That's it from my side. I don't have anything else to say. So if you guys have any questions, you can let me know now, or you can email me. I know it's pretty late at night.
Hi, I've got a question.
Sure.
Yeah, firstly, thank you so much, man. This was quite insightful. So in the example that you gave, you had your primary question being, is there a difference in height between guys and girls?
Yeah.
And then your secondary question was, how did that change over the years, right?
Yeah. Yeah.
So obviously we want to have a good quality and worthwhile study, but like you were saying, we also want to balance the work and time that we put into it. And that secondary question, well, firstly, that your primary question was quite a good one. It's like a cross-sectional thing. It was a snapshot, so pretty
Yeah.
quick to get those results. But your second one added exponentially a lot more work to it, because it means measuring it for another 2-3 years down the line.
Yeah.
How necessary is that to have a secondary question?
It is not necessary. It is not necessary at all to have a secondary question. But the idea I was trying to say is that, or I was trying to bring to everyone's attention, is that research can change. In my experience, we always start with one question, and then I go and meet my surgical supervisor and I come back with 11 questions from him. And it it depends on the researcher, it depends on you, whether you want to take up that question. And you cannot just go to your surgeon and say that, oh, I don't want to take up this question. But what you need to do then is to find out how much time it will take. Is that time viable for you? Is the is that question, answering that question, improves the quality of research or not? So those are the questions you need to ask yourself and find answers for, and then go back to your surgeon and then say that, okay, these are the things I have come up with, and I either take that challenge or I don't take that challenge. That's the idea I was trying to uh, put across. You don't have to have three questions. One question is enough if you at your stage at the moment.
Okay, cool. Thank you so much again.
No problem.